In this video I'd like to provide a really quick reminder of some results to do with differentiation, but then try and get on fairly quickly to anti-differentiation or to finding integrals. So to do this, really we're just going to need to practice lots and lots our results for differentiation, and we've got some of those which are results to do with specific functions, so differentiating, these are just off the formula sheet here, so differentiating rational indicial functions like that, differentiating exponentials or natural logs or trig functions. Don't worry about these ones down the bottom, you won't have seen those, we'll come to those a bit later in specialist maths. So there's those results, but then there's also the results for composite functions, so the chain rule, for products of functions, or for quotients of functions. Let's do a quick example just to remind ourselves how we might use those. So let's say we've got the function y equals x to the fifth times sine x. Hopefully you can recognize that that's the product of x to the fifth and sine x. So we'll be looking at our product rule. And if we use this form over here, we'd be saying if our product is u times v, our derivative of that will be u dv dx plus v du dx. Maybe for this one, since it might have been a while, let me actually sort of put the steps in and specify a bit more. So we're going to say u is x to the fifth, v is sine x, then du dx is 5x to the power of 4, and what's dv dx? The derivative of sine x is just cos x. So dy dx, according to our product rule, is going to be equal to u times dv dx plus v times du dx. So substituting in, u is x to the fifth, dv dx is cos x, plus v, which is sine x, times du dx. I might put them in the other order just because they'll be a bit easier to write that way. So that's v, which is sine x, times du dx. Now we could factorize that if we wanted. Let's just quickly do that. But really, this is sort of a bit cosmetic at this point, since we're not doing any more with it. That should be x cos x, shouldn't it? Because I've got another factor of x there. So let's make that x to the fourth times x cos x. And this would be 5 sine x. Alright, so it's a quick reminder there of differentiating. So I want to think now about that process of anti-differentiating. So let's consider something like, let's just say, something like x to the power of 5. If I said, what is the function or the expression that after differentiating would leave me with x to the fifth? So when I differentiate, I'm saying, what do I get after I differentiate that? But when I anti-differentiate, I'm saying, what must I have started with, which after differentiating would lead to x to the fifth? So in other words, another way of sort of expressing that would be to say, the derivative with respect to x of what is equal to x to the fifth. So what's the thing that I must differentiate? Well, there are some results for this and a number of other functions, but thinking about what we do, first of all, we would realize hopefully that it would need to be something to do with x to the sixth, because when I differentiate it, it's going to reduce its index by 1, isn't it? So thinking about what would happen if I differentiated x to the power of 6, we would get 6 times x to the power of 5, wouldn't we? So if we wanted to just end up with x to the power of 5, I'd need to take 1/6 of that. That would give me 1/6 of this, which would be equal to just x to the power of 5, because 1/6 times 6, that would cancel out there. So in other words, I could say, so let's take that 1/6 inside there, and we will have 1/6 x to the power of 6 is equal to x to the power of 5. Now, you might need to sort of pause and actually just do that for yourself. Just convince yourself that when you differentiate that, you do indeed get x to the power of 5. So, not surprisingly, the process of anti-differentiating for a fairly simple function like this is going to be the inverse of the process of differentiating. So our rule for differentiating, if we go back up here, our rule for differentiating an expression of that sort, x to the power of n, was to multiply by the power n and subtract 1 from the power. So when we differentiated, we multiplied by the index and took 1 away. So think about what the reverse steps of that are. So if I differentiate x to the power of 5, I multiply by the power and take 1 away from it. So if I was to anti-differentiate, and the symbol that we'll use for that at the moment is called the integral symbol here. So if I was to integrate, and the dx just goes on the end, so that means anti-differentiate x to the power of 5 with respect to x, in the same way as this means differentiate x to the power of 5 with respect to x. So anti-differentiate x to the power of 5 with respect to x. So the inverse process of what I just said, here we multiplied by the power and then took 1 away. So let's start with the taking 1 away. The first thing we'd need to do would be to add 1 on. So onto the 5 we add 1, which becomes 6. And then we divide by the power. So the inverse steps in the reverse order, here it was multiply by the index and then take 1 away. So when I anti-differentiate, the first thing I do is add 1 onto the index and then divide by that index. Now that there is the same as 1/6 x to the power of 6, isn't it? So there's a way of anti-differentiating our functions of that form. There is one more thing that we need to say before I just talk about some other rules, and that is that if I said to you, what is the derivative of, we'll use 1/6 again rather than, what is the derivative of that? You would hopefully say to me, well, the derivative of that is x to the power of 5, but what's the derivative of this here? Well, what's the derivative of this here? 1/6 x to the power of 6 minus 25. Well, what's the derivative of that there? So the point that I'm trying to make here is that the derivative of all of those is equal to, all of those have the same derivative, which is x to the power of 5. So when we anti-differentiate, if I say anti-differentiate this, how do I know which of those, or any infinite number of other possibilities, I'm talking about? And the fact is I don't. And so what I do is that I add what's called the constant of integration onto my antiderivative. So I say it's x to the power of 6 over 6 plus c. C meaning any constant, any number value, because the derivative of any constant is going to be 0. All right, let's look at some of the other ones that are on our formula sheet. Okay, now this column, or this image that I've put here, is a column on your formula sheet that is in fact exactly beside this column up here. So these two here, when you look at them on your formula sheet, that's the left-hand column and that's the right-hand column. And this top one here lines up with this top one here. So this one says differentiating something of the form x to the n gives you that. The one that it lines up with says anti-differentiating x to the n. Well, I add 1 onto the index and divide by the index, and then I have a plus c. Think about another one. So for example, here I know that the derivative of the natural log is 1 over x. So working backwards, I should be able to say the antiderivative of 1 over x is the natural log of x and plus a constant. So that's the third line here. The antiderivative of 1 over x with respect to x is equal to the natural log of x plus c. Now we'll come to some of these in later time, so we don't need to sort of worry too much about them. If the derivative of sine is cos, then the antiderivative of cos must be sine. So that's down here. Antiderivative of cos is equal to sine x plus any constant. and the antiderivative of sine is equal to negative cos plus c. We know the derivative of tan is sec squared, so the antiderivative of sec squared must be tan. So there's all of those there. Alright, let's consider an example just before we finish up with this video. So let's go as examples, find the antiderivative, or we could say find the integral. And we'll talk about a couple of different types of integrals. So let's say find the antiderivative of 3x squared plus 5x minus 2. So the notation that I could use here is minus 2 dx. So the integral symbol and the dx sort of go together to say we're anti-differentiating this expression here with respect to x. X is the variable. Now if we did this term by term, we'd say, okay, well that's 3 times x. We need to add 1 onto the index, and we need to divide by that new index. So the antiderivative of x squared is x cubed divided by 3. Then the next term, the antiderivative of x, add 1 onto that index of 1, it becomes 2 divided by 2. And this constant here is really x to the power of 0, so it becomes x to the power of 1 divided by 1. And I need to say, well, there could also be any constant on the end. So I could simplify this one a little bit, cancel the 3's there. I've got x cubed, I've got 5 over 2x squared minus 2x plus c. So just think about what that means for a moment. It's saying when you differentiate this, you get that. When you differentiate this, you get that. When you differentiate this, you get that. But also, if there was any constant here on the end, its derivative would be 0, and therefore anything of this form would differentiate to give that expression there. Alright, there's one. Let's do another one, maybe with a trig function in. So what if I was trying to find the antiderivative of cos 3x. So when you differentiate cos or sine, and you have something like this where there's a, instead of just an x, I've got a 3x, or it could be some other function in there, I sort of need to use the chain rule, don't I? So I'm saying the chain rule for differentiation, if I was differentiating something like sine 3x, which we might think is the antiderivative of cos 3x, that would be a good place to start. If I differentiate that, then by the chain rule I will get cos 3x. But remember, by the chain rule I also have to multiply by the derivative of this, which is 3. So in fact I get a 3 times cos 3x. So here when I'm anti-differentiating cos 3x, I need to recognize that the antiderivative of cos is sine, but I also need to divide by that 3 that would come out from differentiating 3x. So there's the antiderivative of cos 3x is sine 3x over 3, or we could say 1/3 sine 3x. Let me write it that other way. So, or 1/3 sine 3x plus c. Now, this year in both methods and specialist, you'll have lots of practice with anti-differentiating. At the moment, we just need a bit of an introduction to it so that we can start to become familiar. So maybe if you're a bit sort of stuck on that, for a start, convince yourself that differentiating this does indeed give you cos 3x.